2.766, yada, yada, yada. Okay, so that's why we have our terminal action. Because I had noticed right around about
We're
7
starting off with the
significant
memes
digits,
from the past.
a lot of things kind of start to get wonky. I'm not saying that's one of
Oh my
the
god, we're
reasons
lagging.
past couple of years, back around 2019, when NIST redefined SI, they were trying to make it more coherent to line things up. It may have been a factor. Speculation. Okay, all right. So now that we've got the speculation aside, as we can see from the title of this video, basically, how can we reconcile the many worlds interpretation of quantum mechanics with eternal cyclic cosmology? Well, you all know what that means. We conjecture ahead.
Although this is going to be weird, and it's going to be about a different.
Title of the conference was something like "Ground Truth" or "Turtles All the Way Down," and so it seems as though there's one Ruliad. I don't think it rules them all, and it might be just hyper-rulial turtles all the way down.
Yes, it's on the back of an infinite number of hyper-rulial turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
Hey guys, what's going on? Memes here. So, yes, as we were just discussing, welcome Fractal. Yes, we're going to discuss about the minimal arena. Somebody's been doing their homework. There's no official homework. But, essentially, I've been thinking about this. I may or may not have mentioned this. Hey, welcome, awesome one. Yeah, yes, Squirtle Power for the win. But as far as everything goes, I'm listening to it, and this is the confusing thing. People are talking about the multiverse and everything. I'm like, well, isn't universe by definition one? That's why very often I'll try to remember to say a realm of persistence, our observational universe, our universe as we know it, because we should be precise in our language. I learned that from Professor Peterson. But as far as all this goes, let's just jump into it. The real quick 30-second overview is one of the things we ran into. It's like, all right, so we're doing a measurement. It's going to be a collapse of the wave function. Oh my God, what's going on? And one of the big things with Professor Carroll will say is like, no. It just every time it branches out. I'm sitting there. I'm like, so what you're saying is we go from our universe as we know it. We do a little. He literally has an app on his phone. There's an iPhone app where literally he does a measurement needs, asks the audience, do this or that. It's like, all right, the universe basically just branched off. You're like, Nani? How does that make any sense there? At least if you're going to go by the principle of least action or just energies and stuff like that, trying to conserve it, it's like, well, that doesn't really seem that into it. But apparently the math works. I haven't gone through all the maths and everything. But essentially, one of the interpretations is that's why they call it the many worlds and not necessarily the multiverse, so to speak, as many will colloquially say. But the interpretation that you can have is, I remember one of his videos at one point, he's like, well, if, I tried to find it. I couldn't find the exact spot there. But he's like, well, when you're dealing with infinity, that's a long time. So I'm like, he's saying that. I'm like, I kind of had this model and hadn't really presented it before, but I remember what that had told me. And I'm like, just by interpretation, I'm like, this, if it's eternal, eternity is a form of infinity in the form of time, so to speak. So I'm like, well, if it goes on forever, basically, if given enough time, anything that can happen will happen. I'm like, just logically, I'm like, okay, so if everything was different except the measurement of this one thing, I'm like, what? Well, if you're dealing with infinity, I mean, like, it just seems crazy. You're like, how could this ever add up? And then it's like, well, if given enough time, the universe, so to speak, as we know it, will be in the exact same state. Change that one thing. I'm like, what? Well, if it's infinity and you have enough time and everything's going to cycle through, I'm like, technically that will eventually happen. When will it happen? I have no idea. Maybe you can do the calculation. Oh, God. I'm going to have to do that calculation at some point. Oh, at least a rough estimate. Incompleteness there. Yes, we're going to, we won't get it. Many worlds. It was brought to our friends at thereader.mitpress.mit.edu. Because we should try to go for sources that at least people generally agree upon everything. If I'm going to conjecture some totally crazy idea, well, we'll see. That's the thing. A lot of folks saying, "Well, space is infinite." That just kind of, I mean, you could say if you're going to be reknitting it, so to speak. I know Professor Wolfram goes into where for rewriting the hypergraphs and everything like that. Well, if you do it, is that new space? Are those nooms atoms of existence or eames, which by their definition are pre-mimetic? So, the many worlds theory explained. Yes, they go through there and looks like some mirrors and everything. Oh, you can listen to the article too. Cool. Quantum physics is strange. Now, at least it is strange to us because the rules of the quantum world, which govern the way the world works at the levels of atoms and subatomic particles, the behavior of light and matter, as the renowned physicist Richard Feynman put it, are not the rules that we are familiar with. The rules of what we call common sense. Anytime you can inject in Professor Feynman, why not? The quantum rules, which were mostly established by the end of the 1920s, seem to be telling us that a cat can be both alive and dead at the same time. Well, a particle can be in two places at once. But to the great distress of many physicists, let alone ordinary mortals, nobody then or since has been able to come up with a common sense explanation of what's going on. Well, thoughtful physicists have sought solace in other ways, to be sure, namely coming up with a variety of more or less disparate remedies to explain what's going on in the quantum world. Okay? The quantum of solace. I see what you did there. A little Bond reference, I believe, there. So basically, you generally go through, you're trying to figure out the probabilities of what's going on and everything. There we go. You have heard of the many worlds interpretations, MWI, that chances are that you think was invented by the American Hugh Everett in the mid-1950s. Okay, in a way that's true. Well, basically, they go through Schrodinger, Erwin Schrodinger, basically it kind of, I mean, he came up with the Schrodinger equation and everything. Okay, so my big thing is I like Professor Carroll's example when he uses the sleeping gas. I don't know about you all, but I'm pretty sure I've seen a cat in a state of both like awake and asleep at the same time. And their eyes just kind of open there, but they're not really coherent. It's weird. I like cats. So where do we go? Yeah, people have been arguing about this for years. So let's not belabor the point. We go to our friends at Wikipedia. Take it for what it's worth. The many worlds interpretations, the interpretation of quantum mechanics that asserts that the wave function is objectively real, and there is no wave function collapse. This implies that all possible outcomes of quantum measurements are physically realized in some world or universe. In contrast to some other interpretations, such as the Copenhagen interpretation, the evolution of reality as a whole in MWI is rigidly deterministic and local. Many worlds is also called the relative state formulation or the Everett interpretation. So basically, as we're going over there, yes, Kali, that's what because my thing is, it's it really kind of sounds a lot like neutron decay cosmology. I think we're talking about a lot of the same things here. I still want to get you and Brad from the Sonic Gravity podcast on, because I'm hearing so many things, and you both know things that I don't know, and I want to continue to learn to try to figure out what's going on. Well, because humanity needs a win. And if we can do it now because we have the technology to collaborate, I think we should at least give it a shot. But the long story short is, well, let's go over, where are we? Well, no, wrong one. This one. Okay. It's, as I'm in an articulation gesture right there. What the heck am I saying? Hold on. Let me back up. All right. Okay. So the whole claim is, yes, my fantastical drawing here. The premise of the model is our universe as we know it is ginormous. Basically, we're talking about 10 to the 32 meters. I don't know if that's radius or diameter. I'm leaning towards a radius there. At least we're in the same ballpark. What is that? That you literally just take the magnitude of the Planck temperature and you just slap meters on it. It's crazy. It sounds crazily simple. I still need to finish going through all the math and trying to understand what's going on, but at least the conjecture and the terrifying thing is it seems like different observations, whether it's JWST or perhaps even some are saying the cosmic gravitational background. I'm not going to claim that. It just seems like if it's twice as loud as we thought, and there seems to be a lot of it, it's like, well, if that's a frequency where we think it's supermassive black holes coming together, perhaps overcoming the final parsec problem, so it's because how does something too big get there? People have conjectured it can happen. Well, if given enough time, anything can. Again, could just be that. And if our realm of persistence, so to speak, is a heck of a lot larger than we thought, there might be a lot more of that going on. Kind of like if you're seeing redshifted galaxies, and I'm going to make a crazy claim here, we're probably going to eventually see redshifts even higher. Just a thought. Just a thought. Hey, welcome to Chairman. Thank you for joining. So basically, the whole claim is you get about 10 to 32 meters. So at least from our current observable universe is about 10 to 26 meters. So that's 6 orders of magnitude. So you're talking like 168,000 times larger. So if you can do your measurements, things are probably going to look pretty flat from wherever we are. We're probably somewhere in here. So here's the claim. I'm not going to say the Big Bang didn't happen. Some folks are saying there's a second Big Bang. Basically, at about 10 to the negative 8 meters, there appears to be some may say a cinch point. Perhaps I used to do some maintenance, so you'd have kind of like a lock pin that just kind of goes in, sets things together. I also kind of think, and Kali really helped turn me on to this. I think neutrinos are kind of like that lock pin in particles. That's something completely different there. Or is it? I don't know. But the claim is at about 10 to the negative 8 meters, you have a cinch point, which is going to be the complement of a hyperbolic figure 8 knot. So what is it? Let's go over. The only reason I had this here is just so I could click that. I need to throw these all in notebooks and everything. Figure 8 knot complement. All right. Oh, look. This is from our friend Professor Hagen segment. I got to put it in the actual doobly. Okay. So the whole point is, and you can articulate this. We're going to assume it's probably going to be kind of sphere-like. So the whole claim is essentially, we go back over here. This tiny little thing in here is going to essentially be this. So what happened? Oh, look. When you, so basically, Thad had told me at one point you could technically go in the vortex. Coincidentally, the vortex, it's about 10 to the negative, throat is about 10 to the negative 50. I still need to double check. I think it might actually correspond to our estimation of the radius of a neutron. I need to double check all that, which is very interesting. Just again, I get conjecture. But the claim is at one point, as you can see, you can go down this, but that rest again, those are just cut out so we can kind of see the articulation going on inside. That would essentially be like a sphere, so to speak, or technically a torus with a figure 8 twist in it. That's really what it is. Something we didn't know about recently. It's generated by that action there. But the claim is essentially at some point, space-time literally in and of itself, as we know it, my best interpretation what I've learned from Thad is you go in at some point. So, okay, up here, I know I'm jumping around. Whatever you have there, it's just going to be emerging with quark, gluon, plasma, neutrons, and everything. It's going to be coming out extremely hot and dense. Why? Because what's being fed in at the end of a cycle, so to speak, probably going to be some potentially hypermassive black holes. And I conjectured, well, there'll be monsters out there. Because if you start with whatever a hard quark, gluon, plasma, a bunch of neutrons, high velocity, at relativistic speeds, decaying out, essentially, apparently increasing the volume of space-time. As it may kind of look like an inflation. I don't know. Hot, basically start, kaboom. Okay, everything as we know it basically goes out there, and everything eventually congeals into galaxies, planets, and we're here as we know it. Eventually, you start getting like these different superclusters and everything. And if it's kind of like a fountain enclosed in a snow globe, kind of like you shake it up, everything's kind of going around. Eventually, it reaches a point of maximal density. Thank you, Kali, due to gravitation and everything. And if a black hole, I know I'm going to make a lot of people angry with some conjecture about black holes in a little bit. Not today. But then the black holes themselves essentially get turned inside out here. Why? Because they're flying in through one side, it's getting sucked in, being just completely just, I don't know, kind of like a cosmic blender, if you would, and then released back out. Things essentially would cycle around. And if this is balance and flowing through all, there is balance, at least according to the Gray Jedi Code. It looks like this might actually be I believe it was a Cardano machine of the third kind, because they say perpetual motion is impossible. Caveat: there may exist a potential system that could do it. Now, it wouldn't generate more energy than what it had, but it would be able to continue. I'm like, if there did hypothetically exist such a potential Cardano machine, wouldn't it be like the universe as we know it? Like, wouldn't that be a pretty prime candidate that we could see? And even Professor Wolfram at one point, I'd asked him, it's like, well, if our universe like runs for computation, like, could it be Turing complete? And I think he gave the caveats. It's like, well, it would need to be enclosed and be finite, perhaps in space. I think he may have actually said eternal in time, something like that. It's like, well, if we can go through all the, I don't know. Is this the computational equivalence of the Ruliad? I don't know. All I know is it's a double cover of the Geese King manifold, which is the minimal, smallest volume complement of a non-orientable manifold. I believe that's the Wikipedia definition. Its first homology group is the integers. If you got the integers running and another manifold doing the integers the other way, I'm like, is that an object that is potentially run all possible computations? And again, totally freaking crazy, but I'm like, it's a tiny little thing in there in our absolutely ginormous realm of persistence as we know it. What the heck? Oh, I had some other tabs open. Oh, and also to explain this here, yes, I have this crazy thing. This was a geometric derivation of the Einstein kappa from within general relativity, and they have it's like gravity, big G, this, that, and they have it out to about 14 significant decimal places, maybe 13. This derivation gets it to, I think, within 1, so it's like either 12 or 13 there, and then depending on your variation in gravity, literally right around 6 or 7 significant digits. You could go either way and stuff, but this is an interpretation that I actually liked one of the other ones, but the more I think about this stat, it pointed this out for a number of reasons, which we'll get into. But basically, the answer, okay, so we go over here. So what is this? Okay, so your standard 8 pi, and then basically we've got gravity. Oh, let's go over to Einstein kappa. Einstein kappa. Okay. You don't see much about this, which is interesting. Yes, we're scaring people off with the equation. But the whole thing is here. This is one of the few places you see it. The Einstein gravitational constant is defined as, this is the C4 convention, because the speed of light raised to the 4th. So kappa is equal to 8 pi g divided by the speed of light to the 4th. And it comes up to this number here. And it ends up being negative 43 newtons to the negative 1. So you're going through, it's like, okay, so we did that derivation. So if you throw the units in there and you cancel them out, because Dad just knows how to do that and everything, you end up coming out with Planck time squared. So you get your 8 pi. So you basically got, looks like 2 spheres, maybe 4 circles if you would there. So the Planck time squared. So again, we're using the universal binomial factorization equation. What is that? It's the equation that takes stuff, the dimensional ingredients, utilizing Planck units, and it's doing a thing. It has an action. So here's our stuff. Stuff is the Planck times squared, and that's all over. This is the Planck length, and this time the Planck mass. That's by 2 spheres. Very interesting. Double cover. I'm just saying, probably a coincidence. And then we basically have our inversion boundary, because the whole point of this is, well, something I actually got from Richard Asner from Wolfram Institute. It's like, when he thinks of hyperbolic space, he thinks of a negative space. I'm like, oh, it wasn't literally until recently. I'm like, I kind of get that, but I'm like, what if it's going through an inversion? I don't know. What if it's being inverted, something like this? And again, just that's what the model seems to be based upon. Hey, welcome, Sigma. Good to see you, my friend. Good to see you. But, and again, I'm gonna be just honest. This is conjecture and stuff. This is a completely crazy idea. Every once in a while, though, crazy ideas end up being true. Okay, dimensional ingredients. So basically, we have our inversion point, because right around 7 significant digits, coincidentally, Planck mass times the Planck length divided by the Planck charge squares, happens to be precisely 10 to the negative 7, which is very interesting. And when going down the Wolfram hole long enough, you start seeing the constants of nature right around 7 significant digits. Don't quite. Is there a reason why we only have like the Planck units at least measured? I know I have 14 digits there, but see, those are assumptions. But the Planck units, according to NIST, we only have it up to 7 significant digits, and then we still have 2 significant digits of, we kind of think. And they did also redefine SI to make the system more coherent back in 2019. And they finished the rollout, I think, towards summer last year, I believe. Okay. That was a lot of bloviating. But I realize some folks are new here, especially if they are watching temporally in the future. So we got basically 2 spheres, or 4 circles. Planck times squared, divide by the Planck length, as well as that by the Planck mass. Cool. And then basically we have our terminal action here. That's 1 plus whatever we get here. This is a Judd 2. What's that? It's the second answer to the hyperbolic vortex equation, or you might refer to it as the second fine structure constant. It's a lot larger, and it seems to have something to do with the bulk in at least this, computation of the Einsteinian kappa. It happens to raise to the 5th, which this happens to be a 5-dimensional model, because as far as we know it, our realm of persistence, our colloquial universe, aside from something dimensionless, such as the fine structure constant, can be made up of 5 ingredients: time, space, mass, charge, and temperature. Give it a shot. It might be current, but that's a derivation of charge and time, and I think maybe length. I don't know. That's what Wolfram Alpha is for. It literally tells you the dimensions. But we have that to the 5th. It's a 5-dimensional model, which is interesting. And then we have this unit over here, which is fascinating. And then we multiply it by the magnitude of the Planck mass times the Planck length divided by the Planck charge squared, which comes out to be 10 to the negative 7. So for notation, we just divide that by 10 to the 7. Gives us this number here, which it's 2844. I'll grab an extra significant digit. Let's reload this. It basically comes to within 1. So it looks like it more or less nails it spot on. But aside from that, we're looking for a story, because you can kludge whatever you want and come up with whatever numbers. And it's even for a while, I'm like, before I see this 2849, so I think we're off. So 284, yeah, 4. Okay. So it's right around 13th significant digit. It's okay. Not too shabby. But what I really want to show you all is What the heck is that number there? That number that popped up, let's literally just go in there. We'll copy. Oh God, I did it wrong. I hit something. It's all right. The benefits of live internet, everybody. You have a good old laugh. Okay, so we get that. Copy it. Boom. Throw that in there. Go Wolfram Alpha. What might you reveal that was hitherto unseen? Da-da-da. Oh, what's this? That's literally the X we needed to solve for to figure out which would get us as close as we can. So I did a video on that the other day. I'm going to shorten it down to about 5-10 minutes. So it'll be more coherent rather than like 28 minutes long. And I know oh God, it's going to be another one of those videos. This right here. So at least within a model that uses 5 dimensions. So we need to subtract out something. So we have 5 CET divide by 44. A second. 44. I mean, isn't that this is the name of Thad's most recent book, 44 Derangements in the Shape of Persistence, which happens to be the number of derangements or permutations of 5 dimensions, 5. Basically, I think you do was exclamation point 5. I think that's it. The factorial is, I think, like 120 or something. But when you derange 5, it comes out to be 44, which is interesting. Okay, let's go into the deepest of lore. What the heck is that CET? CET is the Embry-Trefalin constant. What the heck is that? Well, the funny thing is, even Math World doesn't bring you right there. Random Fibonacci sequence? Wait a second. Fibonacci, that's supposed to be those spirals and that whole counting thing. Oh God, what type of Wolfram hole are we going down now? Let's go down it. It's really short. Okay, consider the Fibonacci-like recurrence. So you got, this is just how you do it. Name it what you want. A sub n equals plus or minus a sub n minus 1 plus or minus a sub n minus 2, blah, blah, blah. Where that's going to the sign. So each sign shows it independently at random with a probability of 1/2. It's very interesting. Wait. Plus or minus? What does plus or minus have to do with something? Huh. Wait a second. Plus stuff coming out minus. I mean, Kylie's been talking about neutron decay cosmology. I'm like, plus neutron minus 8. It's just doing a half there. It seems to be an iterative sequence, which is interesting. Again, just conjecture. I'm not saying this is how things actually work, but sure would be sweet if it did. Okay, so when you take it to the limit, and it gets even more fascinating here, that sigma b is the limit of n approaches infinity of x to the n raised to the 1 over the n, exists for almost all values of b or beta. The critical value of b such that the sigma b equals 1 is given by this right here, 0.70258. It's sometimes known as the Embry-Trefalin constant. Okay, it's a constant, but notice this, all those constants like the Giesking constant, the figure 8 knot hyperbolic volume, we can calculate those out to as many significant digits as we want or want to allocate computational time. Hey, welcome, Wow. Thank you for joining, my friend. But I'm looking at this. We only have it to 5 significant digits. Isn't it 2023? Apparently, the deep lore of this is it's extremely hard to calculate because literally you're doing it's like, all right, it's supposed to be random, so you gotta go plus minus, and you're taking it to the limit to infinity. I guess to get another significant digit, we need to spend a heck of a lot of computational resources to try to figure it out, but this is pretty good. It also happens to be a solution to at least the claim is the geometric derivation, the Einsteinian kappa here. So to bring it all back together, I know I realize I blew it on. Okay, I'm not going to say exactly how we got here, but the conjecture is this appears to be how we persist. So we persist in balance. Basically, energy, once it forms its basically most dense state in everything, it doesn't necessarily need to be that. No, but if you get a whole bunch of supermassive, hypermassive black holes going together and everything, things are probably going to go into them. It basically then goes through a cosmic blender, if you would, basically being sucked in and spewed back out as what would appear as a Big Bang, perhaps a kaboom, kinetically accreting baryonic oscillatory origin module or something like. Oh God, such a forced acronym, but I don't know. It seems like it would explain a lot, and if it is eternal, let's just say that measurement that Professor Carroll did on his phone for the electron, or whatever derivation you're going to do, asking that person out on a date, spraining your ankle, getting that last little bit of peanut butter from the container and not scraping up all the plastic. Ugh. Yeah, but at some point or another, it probably will happen because, again, that's one thing I learned from Professor Carroll. It's like when dealing with infinity, that's a long time. That's all I got for right now. Thank you all for watching. Peace, everybody. Take care of yourselves. It's a wacky and wild world out there, but I think the best is yet to come. Take care, everybody.